On that. We were talking about supply and demand last time, and today I kind of had a choice to try to squeeze in a little bit of elasticity. I was tempted to possibly throw it out, but then it ties in so nicely. There was some other circumstances where I just decided at the end of the day, let's just move it to Monday. So that's where we're at. We're going to just move it to Monday rather than try to do some combination of that. It seemed easier. So we left off setting up some qualitative analysis. So far, we have mostly done a qualitative analysis of supply and demand. What do I mean by that? I mean those little arrows that we've been working with. We increase price, so for example, we increase price, it leads to a decrease in the quantity demanded. We increase price, it leads to an increase in the quantity supplied, ceteris paribus. We have an increase in income, it leads to an increase in demand for a normal good. Things that we have to know for the next test. So what I mean by qualitative is just the direction of the changes. So these little arrows here, an increase in this leads to a decrease in this, right? But unfortunately, an economist doesn't get paid six figures to go to the CEO of Pepsi and say, listen, if you increase price, you're not going to sell as much. Right? So we have to add this quantitative stuff to it. That's where the economist starts to earn the big bucks, is by quantifying some of that. So chapter 4, we now will quantify our analysis with elasticities. With elasticity. So for example, what the type of statement we want to be able to make to that CEO is that if you increase price 10%, that's going to lead to a 24% fall in sales. So an increase in price of 10% will lead to a decrease of 24% in sales. How do we start to make these quantitative statements where we're increasing 10% and that's causing a 24% fall? We do this, for starters, by looking at the elasticities. So let me start you off with the definition. The first one we're going to look at is the elasticity of demand, which I'm going to use the notation with a sigma subscript D. So kind of that pointy little summation type notation with a D. The elasticity of demand is simply a number that shows the responsiveness of quantity demanded to a change in price. A number that shows the responsiveness of quantity demanded to a change in price. Okay, so a couple key points I'll just highlight right out of the gate so that they're good and crisp in your notes, is that the elasticity of demand measures movement along a demand curve. So quantifies movement along a stationary demand curve. No shifting, because what we're changing is price, and we learned last time that that was a movement along the demand curve. So if you ever can't see way back there, just shoot up your hand. I'll try not to get myself in a pinch down here, but quantifies a movement along a stationary demand curve. So let's start by looking at a couple demand curves. Let's put two graphs side by side. And the graph to the right, I want you to put a relatively flat demand curve. The graph to the right, the graph to the left, relatively flat. The graph to the right, a relatively steep demand curve. So the slope of the demand curve makes a difference on this responsiveness business. Which demand curve do you think is more responsive, i.e. more elastic? More responsive, more elastic. Situation A or B? B. More responsive? Everybody agree with that? Abby says no. Why? Why do you say A?
Because even just a small change in price makes a huge difference in how much people want.
Okay. Those of you who are in the B camp, what were you thinking? Thinking never mind. You like that explanation. Okay, so one way to think about this is, what are we responding to? What I talked a little bit about it before. What's the independent variable? What's the dependent variable? What's the independent variable? Price or quantity demanded? Price. Independent is price, right? That's the driving factor. Now we had other variables that were important, don't forget, because we're going to come back to those later. Income, price of related goods, all the things that shifted the curve, those are important variables too. But here we're looking at price, and how does price change? How do consumers respond to price changes? All right, so on this graph, if we take two prices, let me just pick a couple numbers here, of $8 and $6, just making some numbers up. Price, quantity. Make sure we got our labels down here. And I then track over to this demand curve and observe that quantity. I truck down to this demand curve. I observe this quantity. If I had these measured on the same distances, which we don't always do, but on the vertical axis, and I go from this demand curve, from here to here, I think we see what Abby was talking about, right? A bigger response. So imagine that these were equally spaced. Here, consumers are responsive. Here, consumers aren't very responsive. All right, so demand curve A is said to be more elastic. So let's write that down. Demand curve A is from market A, I guess, if we got apples and bananas here. Demand curve A is more elastic. We have a bigger response, more elastic than B. Okay, so let's suppose that the quantity demanded at $8 was 100, and the quantity purchased when price fell to $6 was 140. So there's a 20 unit increase. What I want to do next is calculate a number that shows the responsiveness of quantity demanded to a price change. So now we're going to get into a formula, which reminds me to talk about today's math review time. What time did we say we were going to do? Those in the math? No, I talked to some people after class. 3 o'clock. So that's another thing to jot down. If you are interested in a math review, some of you are required to come. If you have not passed your quiz, that appendix quiz, you are required to come. But today at 3, at actually I'd like to go to the room across the hall. I'm wrapping up a class there, so just kind of come up here, but it'll be across the hall, and I'll just stay in that class. So AD 301. We're in 302 now, so we'll just be across the hall. Oh, I'm sorry. Thank you. Board science. Thank you. Okay, and then anybody else who wants to come, what I'm going to do is review, and this is great review for the test, but so as far as the mechanics of the math, but really go back to slope of curves, the shifts, the graphing goggles, equation goggles. We'll just kind of really hammer out some of those math skills we need for the class. Okay, so anybody's welcome. All right, so this number is a simple ratio of the 2 points on the demand curve. We're going to calculate the percentage change in quantity as well as the percentage change in price. So this is just one of those things we might just have to bite the bullet and remember it. So here's that number. The elasticity of demand is equal to the percentage change in quantity demanded divided by the percentage change in price. Who remembers the percentage change formula? Give it to me in the difference between what? Like let's just stick with price here. The difference between 8 and 6, the new price and the old price, divided by the average, possibly.
The median.
The median. Okay, you could take the median or the average. You guys are fancy right out of the gate. And I just want to highlight one thing that's usually the way we do percentages is you take the new number minus the old number divided by the old number. That's kind of what you might have seen in some other classes. In fact, you might even see it in this class at some point. Probably not so much in this class. But if you're in my money and banking class, which John's not here, but there's a couple of you. Oh, Katie there. Yeah, we have that formula is kind of the normal thing. New number minus the old number divided by the old number. But now we're going to use it a little differently. We're going to use the average of the two. And the reason is that if I do a $2 price change and price went up from 6 to 8, the new number's 8, the old number's 6. So it's 2 divided by 6. But if I do a price decrease, it would be 2 divided by 8. You see how we're getting a different percentage change, 2 eighths versus 2 sixths, 33% versus a quarter, 25%. That's a big difference. I don't want that to change. And so how we fix that is to take the average of the two numbers. All right, so for our class for elasticities, it's called the midpoint formula. We're going to take the change in quantity divided by the average quantity. And divide that by the change in price divided by the average price. All right, so just to be completely complete with our formula, we're going to take the new quantity minus the old quantity divided by the average quantity, which, if we do the math, how do we figure out the average of these two numbers? I mean, we know it's 7. Our gut feeling is 7 is the average, but how do we get that? Add them up and divide by 2. So it's actually Q new plus Q old divided by 2 is the average. Divided by, so we'll just blow this thing up once. So most of these problems you'll just do your gut feeling like you know it's 7, but it's good to have this down in one spot at least. The new price minus the old price divided by the average of the two prices. So the new plus the old divided by 2, there's the average, there's that chunk. And there's the formula in all its glory. Yes? The new price plus the old price divided by 2. New price plus the old price divided by 2. So this average is this part in parentheses. Same thing here. So I just kind of gave you all of it in its whole big glory. It's kind of big and ugly, but that's what it is. So let's practice. Let's see if we know what we're doing. What is the elasticity of situation A? What is the elasticity of demand for our A market, the apple market? Maybe I'll just put apples in there. I hate using A's. Apples, and this was the banana market. What is the elasticity of demand for the apple market? So, take a couple minutes. You can work with your neighbor if you're kind of stuck or something. You should work that out on paper. Get out your calculators if you got them. I will allow you to pull out your phone. Just make sure, hopefully it's already set to not receive any outside communications of any sort, but you can pull up the calculator function if you want. What is the elasticity of demand? Yeah. So let's, just to be complete, what did I say? Let's do a price decrease. So let's say the old number is 8, the new number is 6, which makes the old quantity correlated with the 8. So this is QO, the old quantity, and this is the new quantity. First person with the right answer gets an extra credit point. You can just bark it out as soon as you get it. 2. Michael goes for 2. .83. Is that Brinson? Michael.
0.86.
0.86. Who said that?
Right.
Right. .16. Abby. It's like kind of a variety pack. More seconds. How much? 10.3. Name again? 10. Negative 0.86. Huh? Rolodex was not quite spinning fast. You got 1.162, okay. 1.17. All right. So whoa, let's call it good now. I don't know what the answer is, so let's just figure out. I do know this, though. There's only one possibility technically of the right answer right there. So can you narrow that down? The negative one. Well, let's see. There's independent answers. This is a completely unique answer. So there's some other unique answers, but has to be negative. So let's just talk about that for a second. Why do I know that? Jesse, why do you know that? Let's put you on the spot since you came up with this.
Because it's a decrease.
Okay, so it's a decrease. So just because this is going down, so if this was going up, it'd be positive?
Depending on the curve. So, right?
We're still have a demand curve. So imagine if I just switched this to a 0 and this to an n, then it would be positive? Maybe? Good. All right. So Jesse got the right answer, but not the right explanation. Got the right explanation there. So what law tells us that it has to be negative? The law of? No. The law of demand. The law of demand. Holding all of the things equal, an increase in price leads to a decrease in quantity. Negative relationship. A decrease in price leads to an increase in quantity, ceteris paribus. So the demand curve always shows a negative relationship between these two variables. And as was pointed out, if we switch these around and this was the new number and this was the old number, it's a price increase, but that would lead to a decrease there. Yes? Oh, the calculator's negative. Well, there's interpretation issues and communication issues. So. Okay, you just you just ignored that little fact. So you did have the negative. All right, well, that's good. So, what do we got here? So let's see, the elasticity of demand equals new number minus old number on price, but new number minus old number on quantity. So we get 40 over 120 divided by negative 2 over 7. And help me out here, 40 divided by 120 is 0.3. 3? 3. And 2 divided by 7? 0.2857. Those two divided by each other gives you negative
I do have to say
1.17.
You have to cut us some slack on the negative part because you have been telling us, hey, since this is a realistic situation, it's always going to be positive.
Well, we're not quite there yet. No slack at this point, but there's going to be slack later. If it's appropriately defined slack. So negative 1.17, did everybody get that? All right, so maybe we'll give, what was this? Was this you, Bree? With your negative here. All right, so Bree and Abby, well, I just feel like giving extra credit. So even though you were dead wrong, we will. Okay, so now back to Michael's thought. Since we all know that it's always negative, economists tend to speak of elasticities in terms of their positive, or as a positive. So technically on paper, it's okay to put that as a plus if you put the absolute value signs around the elasticity as a reminder. So the elasticity of demand equals this, or if you want, you can do this. The absolute value of the elasticity is positive 1.17. So in fact, that's what we usually do. So as you read through your textbook or something else, we might say the price elasticity of demand is one. It's 2. We usually don't speak that negative sign. So that is a little thing that was invented to screw up students mostly, because then when you go back to do your work, if you forget about that little negative sign, it can kind of come to bite you. If I have you solve some algebra to figure out what this number is, knowing that the elasticity is 1.17, what is the new quantity? So imagine if we had to do a little bit of work around here to solve for one or the other, then you have to remember that whole negative business. Okay, so fun stuff, fun stuff. So this is a straight line. So just to make sure we're all tracking here, what if we look at this number? What is this number? 180. If it's a straight line, it'd be 180. And what would be the elasticity of demand using these numbers then? The new number. So here, A to B. Now let's say from B to C. A, B, C. I'm not doing so good with my B's here. What would that one be? 1.17? Still be what? We'd be using point B, yes. Point B to point C, what would be the elasticity there? Be the same. Why?
It's a straight line, it's a linear.
It's a straight line, so the slope is constant. Along a straight line, by definition, the slope is constant. But just for a little bit of practice, let's do it. I know it's a little bit, just start to work out the numbers. Go ahead, get your pen and paper out, and actually plug the numbers.
So first person with the right answer.
Yes, first person with the right answer gets an extra credit point.
1.17.
Wrong.
Negative 1.17.
Wrong.
Absolute value of
Wrong.
It's the same.
Work it out, work it out, work it out, work it
So we're
out.
going from A to C.
Trust me and work it out. So we're going from B to C.
Okay.
Negative 0.875.
Negative 0.875, Quinn. 0.875 is the Quinn.
Negative 0.05.
Negative 0.05 is the Riley. Negative 0.625. All right, closed. Let's just do it now. See who was right. The elasticity of demand is the new quantity.
none of those are right.
180 minus 40, that's, so I still get that 40 up there. But what changed?
Average.
Yeah, the average. So it's going to change things. So we've got 160 in the denominator here. And now we're going from 6 to 4. The 2 didn't change because the slope is constant, and it's a negative 2. But the average did. Now we're averaging at 5. Answer?
It's negative 0.833.
625?
Yeah, 625.
So Quinn's got supporting Tanner? Everybody got Tanner? 625. Tanner's our winner, huh? Nice job. All right, so negative 0.625, which then in absolute value would be 0.625. So next thing I want to highlight for you is we're going to pretend like the averages then marks the spot. So the elasticity of demand in absolute value at this spot on the demand curve was 1.17. But now we just calculated at this spot, the elasticity of demand in absolute value was 0.625.
So we're supposed to find what is pointing at.
No, nope. We're not going to find it anywhere. We just learned ourselves a valuable lesson here, that the elasticity of demand is different than the slope of demand. The elasticity of demand is different than the slope of the demand curve. So it kind of makes sense now if we start to think about, if you have $1 and I give you another $1, what is your percentage increase of money in your wallet? If you started with $1, about 100%, right? Now, if you have $99 and I give you $1, what was the percentage increase in your wallet for that same $1? About 1%, right? So the percentage change depends on where you're at on changing. Same thing works out here. If we look at a 1 unit change in apples, we can double apples from 1 apple to 2 apple, that's like 100%. But if we come to 180 and we think about adding an apple, it's a very small percentage change. So the ratio of the percentage changes is kind of the key thing that we get with elasticity. And in fact, the elasticity is different at all points along the downward sloping demand curve. So you're going to find those are all over the place. Katie?
Why aren't they in the back?
I just put the brackets around.
Oh, okay.
Yep. So the brackets is absolute value. So I just did that little notation.
Okay, and then, are these percentages?
We're calculating it to a percentage. As long as you are consistent, will you get the same answer if you do 0.33 divided by 0.28 or if you do 33 divided by 28? Same, right? Did you catch that? So this is 0.33. If I change that to a percent, not sure if this is your question, I guess.
No.
33 divided by 28%. 33 divided by 28 is the same number as 0.33 divided by 0.28.
Right. No, I'm asking
Okay.
is like the 1.17 percent.
Oh, another good question. All right, that might be worth another extra credit point. Now that I understand your question, what is 1.17? Let's just run with Katie's thing here. Is it apples? Is it dollars? Is it percent?
Just a unit.
It's just the unit. Why do you say that,
Because I saw it in the book.
Riley? Okay, fair enough. You read ahead, it's worth an extra credit point. Riley gets the extra credit. All right, it is a unitless number. A unitless number. So you're taking the ratio of two things. If I take the ratio of apples, it's a unitless number. It's just a ratio. So there's no units to it at all. We have a ratio of two percentages. It's just a number. So if you go back to the original definition I gave you, you can maybe even sneak this in if you want. I gave you a number that shows the responsiveness. It's a unitless number that shows the responsiveness of quantity demanded to a change in price. Okay. So
what happens if we what does the lower number mean?
the lower number on the formula?
No.
Oh, what is the lower number? Yep, we're going to get there now. All right, so key point. The elasticity of demand and absolute value is different at each point along a downward sloping linear demand curve. Demand curves in real life are not lines, but for this class, they're pretty much going to be lines. Lines have constant slopes, which got us into our first little quirk of elasticities. Despite there being a constant slope, we have the elasticity changing. The elasticity of demand in absolute value can take on a value that's greater than 0, but it have to be less than positive infinity. So the range of the elasticities in absolute value, don't forget the brackets, is between 0 and infinity. Yes?
Would it be infinity equal straight or
We'll come back to you on that. Yes, it's going to be one of those. It's going to be one of those extremes when we start getting into extreme econ. We've heard about the snowboarding and all those extreme sports. You're going to see how economists get extreme here and the implications of that pretty soon. Michael?
So is there a perfect, I mean, this is kind of just.
Okay, you're jumping the gun. Let's get where this is happening. So along the demand curve, if you take the endpoints, go ahead and touch both the horizontal and the vertical axis. In fact, I'm going to redraw that. You can go ahead and draw that one, but I'm going to draw something else too. Okay, leave enough room below your graph to do this. I'll explain why in a second. But the upstairs graph is all I want to focus on for right now. All right, so as we move along a demand curve, it varies between 0 and infinity. There's one point where it equals 1, and I'm just going to spoon feed this to you here. If you take the midpoint between where demand intersects horizontal axis and the origin, find the midpoint, go straight up. That is where the elasticity of demand is equal to 1. Okay. The percentages are equal. Great. That is exactly where we were going with that. So with the percentages equal to 1, that implies the percentage change in price is equal to the percentage change in quantity demanded at that particular point along the demand curve. It's called unitary elastic. Demand is said to be unitary elastic. Now we saw this happen on the example we did. As we moved this direction, which was point B and C, we saw that that number was less than 1. We had 1.17 before. We've got 0.625 after. So along this area of the demand curve, we have the absolute value of the elasticity being less than 1. If that's the case, what's true about that percentage change business? All right. The downstairs has to be bigger than the upstairs. So the denominator is bigger than the numerator. So if this is 10%, this is 20%, right? So the downstairs number is bigger. So the percentage change in price is greater than the percentage change in quantity demanded. Let me jump up here. As we get really close to the vertical axis, what would be the values of that elasticity of demand? What would they be approaching? Something really big here. So like, if we're right up there, it's approaching that endpoint, one of the endpoints. Is it the infinity endpoint or 0 endpoint? 0? Which one's bigger? The percentage change in quantity or the percentage change in price as we get close to that endpoint? Quantity. So it's blowing up on us. So at this endpoint, it's infinity. At this endpoint, it's 0. There's your range of everything in between. If we were right on those endpoints, that would be close. But we never quite get there if we're actually looking at the ranges. So those are just kind of theoretical endpoints. So everything in between, the elasticity of demand is greater than 1, which means that all places along here, the percentage change in price is less than the percentage change in quantity demanded. So when the elasticity of demand is greater than 1, would you say that it's more elastic or less elastic?
More.
More. Why?
Because it's using a broader range.
You're using a broader range of what? What's the bigger range?
Numbers.
The numbers of prices or quantities? prices are big or the quantities are big in terms of percentage changes? Which one's got the bigger percentage change? Quantity. So we're getting bigger bang for our buck, right? A big response in quantity to a small change in price. Responsiveness, elasticity. So this is called the elastic range of the demand curve. This is the elastic range. Whenever the elasticity is greater than 1, and we get a lot of bang for our buck, the upstairs is big compared to the downstairs, we say that demand is elastic. Down here, just the opposite's happening. We change price by 10%, but we only sell 5% more. Or it's a smaller number. This is the inelastic range. So demand is elastic, demand is inelastic. It changes depending on where we're at. All right, so we took some time to draw this little guy down here because I want to measure total revenue on the vertical axis. Now, who remembers what total revenue is? Total sales, sales volume, right? Price times quantity. So if we're a business and we're looking to maximize profit, we're going to take money in the cash register, total revenue. You guys have this in your notes from before. Total revenue minus our total cost. Total revenue is price times quantity. If I sell 100 glasses of lemonade at a price of $1.25, I got $12.50, right? Price times quantity. So total revenue here is price times quantity. It's the interaction of price and quantity. So here, the upstairs graph has quantity and price. Now we're going to look at the interaction of those two things. So if we drop price, we sell more, right? Law of demand says, cut your price, quantity will go up. You're going to sell more. But are we going to have more money in the cash register? Are we going to have more money in the cash register? For sure. And it turns out to be no, this is a little bit tougher issue for people to grasp onto. If you cut your price, it's possible that your revenues might fall. It's possible that they might go up like you were hoping to sell more and actually make more on revenues. But the true answer depends on the elasticity of demand, which is exactly why we calculated it in the first place, or one of the reasons. Total revenue is maximized. I want you to draw a big dot somewhere up above. It doesn't really matter where you do it, but here, when demand curve is unitary elastic, that represents the maximum amount of total revenue that's possible given the current demand curve. And then the rest of it is just a big mountain of cash. And it looks like this. At this endpoint, I want you to come down and make sure that these are connected. So what connects the upstairs graph and the downstairs graph is the quantities. So if this is 1,000 units, this is 1,000 units. The up and the down are linked. That's why they're stacked vertically on top of each other. The next thing to do is just to make kind of a bell-shaped hump curve. Just go up, max it out, and come down. And what you've probably drawn for the first time is your first total revenue function. We got our graphing goggles on, looking at a total revenue function, price times quantity, and how it varies depending on if demand is elastic or inelastic. What's that? Inelastic, yes. So now they follow the ranges, right? And so here's how we use this graph. This is why it's one of my favorites. If you go from point A to B up here, if you go from point A to point B, you're cutting your prices, right? Point A and point B are directly correlated with point A prime and point B prime on the revenue function. As we cut price when demand is elastic, revenues increase. If demand is inelastic, check this out now. Let's go from point C to point D. Doing the same thing. I'm going to cut price, possibly by the same $2 we did before, right? Kind of similar to our $2 deal. Let's cut price, but now when I cut price, point C and point D directly correlate with C prime and D prime on the revenue function. And if the business cuts price there, they're going to bite into total revenues. Total revenues are going to fall.
So the y-intercept is always going to be included, no matter where it's at.
Up here, yes. I mean, the endpoint is theoretically there.
But not.
And here it's just 0. So we have a super high price, but nobody buys them. I get 0 revenue. Right? That point is correlated with no money. On the x-intercept, I give away my product, and a whole bunch of people want it, but I have 0 price, so I get 0 money.
Okay, so on the bell curve, it's 0, 0.
Yep, it's 0, 0 on terms of revenue. So we're just measuring this along the vertical axis here. All right. Wasn't that fun?
Yeah.